Assalamualaikum students. Today's topic is going to be about absolute potential energy. Let us read about it. So what is absolute potential energy? Consider a body of mass m at a certain height h in the gravitational field. Thus potential energy, that is Be, is equal to mgh, where m is the mass, g is the gravitational acceleration, and h is the height of that mass. Let's assume that this is the mass we are talking about on the surface of the earth. When the height h of the body of mass m is greater than the radius of the earth, then the above equation, which is E is equal to mgh, is not applicable. That means the gravitational acceleration is so much less or reduced so that the formula is not applicable. Thus, the above absolute value of potential energy of a body in a gravitational field is needed. For this purpose, 0 point for the potential energy is fixed. What is 0 point? 0 point is a point so far away from the Earth that the force of gravity is negligible. Small, not attracted by the Earth, and hence its potential energy is equal to zero. That means it has no potential energy because the value of g is equal to zero at this point, and the height is too much. So we don't have the applicable formula for here, which is mgh. To compute the work done in moving the body from the Earth's surface beyond the Earth's surface to a very far off distance from the Earth where the force of gravity is reduced, we have assumed that we have taken the body to a certain distance, let's call it r1. So figure shows a body of mass m at point 1 at a distance of r1 from the center of the Earth. As the body is moving from point 1 to far off point n, the gravitational force does not remain constant. That means it keeps on changing when it goes to point n, like this. So how do we keep it constant at certain levels? So what do we do? Here we divide the whole distance into number of small distances, each of magnitude delta r, so that force during each interval remains constant. That means the gravitational field in each interval, while taking it from point 1 to point n, will keep the gravitational field constant at certain levels, like this. So the gravitational field between point 1 and point 2 is same. The gravitational field between point 2 and point 3 is same, and so on until n minus 1 to n. The gravitational field will remain the same. So let us assume we are taking the body from point 1 to point 2, which has a radius, or the distance we can say, r1 and r2 respectively, where r2 is greater than r1 because we are taking it from point 1 to point 2. The distance between r1 and r2 is basically represented as delta r, which means r2 minus r1. And here is the distance between the two distances, r1 and r2 respectively. And we take the average of these two distances as well, r1 and r2. How can we take the average? So r1 plus r2 divided by 2. Now work done between point 1 and point 2 will be given as work done from point 1 and 2 will be equal to average force is equal to delta r into cos theta. That means ft cos theta was converted into average force r, which is the distance traveled by that body from this point to this point, and cos theta is because it is a scalar quantity. Now putting in the value of theta equal to 180. Why? Because the body is moving against the gravitational field. It is moving against the gravitational field. Gravitational field was pulling it downwards, whereas the displacement was in opposite direction. So that is why we have taken the value of theta 180. Let me show you over here the displacement. The displacement is in this direction, which is delta r, and the force of gravity is pulling it backwards. So the angle between r and f is basically 180, and that is why we are putting the value of theta equal to 180 degrees. Now putting the value of cos 180, we get minus 1 right over here, And when we multiply -1 with average force and delta R, we get minus average force and delta R. So putting the values of average force, which is due to gravitation, which is G, which is the gravitational constant, M, which is the mass of the body, M over here, and ME is the mass of the Earth divided by the average distance between the two bodies. Now, when we put that value F average in the above equation, we get work done from 1 to 2 will be equal to minus G small m capital M, which is the mass of the Earth, divided by average radius, or the distance between the two distances, and the difference between the two distances R1 and R2 respectively. Now, how can we find out the values of this average, which is in square? Now, for this, we have to do some calculations. Now, to determine the value of average R square, we have two values already, which is delta R, which is the distance between the two distances R1 and R2, and average R, which is R1 plus R2 divided by 2. Now, what do we do from here? Putting the values of R2 in the above equation, what do we get? We take the R2 on one side and take minus R1 onto the other side. It will be R2 is equal to delta R plus R1. Putting this value of R2 in this equation, we'll put in this equation, what do we get? We get R is equal to delta R plus R1 plus R1 divided by 2. So these two R1s basically will add. So what do we get? R is equal to delta R plus 2R1 divided by 2. So R will be equal to delta R divided by 2 plus 2R1 divided by 2, because we have separated the LCM. We cancel the 2 out. What we are left with, R is equal to delta R divided by 2 plus R1. Taking square on both sides so that we can find out the average R. So if we take the square on both sides, we are applying basically formula of A plus B whole square, which was equal to A square plus 2AB plus D square. Keeping that in mind, we are applying the same formula in the above equation. What do we get? We get R square is equal to delta R divided by 2 whole square, which is the square of, let's assume it as A, plus 2AB, which is delta R divided by 2 into R1, which is B, plus R1 square, which is taken as B over here. Now, neglecting the square term because it is very small, delta R divided by 2 whole square, because delta is already very small. When you take the square of such a small quantity, it becomes more smaller, or we can say it is such smaller values that it will be negligible, or we can neglect it. So what we are left with, R square is equal to 2 into delta R divided by 2 plus, into R1 plus R1 square. Now we are cancelling these two out as well. This 2 and this 2, they can cancel out. So what we are left with, R square is equal to delta R into R1 plus R1 square. Putting the values of delta R over here, which was equal to R2 minus R1, we get R square is equal to R2 minus R1 into R1 plus R1 square. Multiplying this R1 into the brackets, what we get, first we multiply this with R2, and then we multiply R1 with this R1 as well. So what we get, R2 R1 minus R1 into R1 plus R1 square. So it will be equal to R square is equal to R2 R1 minus R1 square plus R1 square. So these two values can be cancelled because one is in positive, one is in negative. So the thing which is left with us is average R square is equal to R2 R1. Let's call it equation number 2. Now put the value of equation number 2 in equation number 1, which was R average square is equal to R2 R1. So it will be equal to work done from 1 to 2 is equal to negative into G m small m, which is the mass of the body, into mass of the Earth divided by R2 R1 and the delta R can be written as R2 minus R1. Now this deviance value can go under 2 R2 minus R1. So it can be written as minus Gm into capital ME into R2 minus R1 divided by R2 R1. We can write it down in LCM method. We can separate them like this: R2 divided by R2 R1 minus R1 divided by R2 R1. So we can cancel these two R2s and R1 and R1. So we are left with 1 over R1 minus 1 over R2 like this, cancelling the values. So what we are left with? We are left with 1 over R1 minus 1 over R2. Putting the values in the equation back again. So work done from 1 to 2 will be equal to minus GMME, which is the mass of the Earth, 1 over R1 minus 1 over R2. In a similar method, we can use it from moving it from 2 to zero point 0.3. We get 1 over R2 to 1 over R3 and so on till we get to point N. So the previous point of R is N minus 1. From going N minus 1 to N, we have the equation W from N minus 1 to N will be equal to minus GME into 1 over Rn minus 1 to 1 over Rn. Now we are adding all these works which we have done from point 1 till point N. So when we add them up, what do we get? From 1 to N, we'll get minus Gm into Me, 1 over R1 minus 1 over R2, plus minus Gme and small m as well, 1 over R2 to 1 over R3, and so on. It goes up till the first value, the second last value which we get is minus Gme in 1 over Rn minus 2 to 1 over N minus 1, and the last value will be G minus Gme, which is the mass of the Earth, 1 over Rn minus 1 to 1 over Rn. Now, if we take this value constant, that means the values of minus Gme, Gme are all constants. So we can basically take them common. They have the same value. So what we are left with? So all of these values, if you see them, one is in positive, like R1 over R2 is positive, 1 over R1, R2 is also in negative. So we cancel these values out, except for the first value, which is 1 over R1 and 1 over Rn. All of the values will be cancelled out in this way. So let's do this one. So these values cancel out and we are left with the work done from R1 to Rn will be equal to minus Gme into 1 over R1 minus 1 over Rn. Let's call this equation number 3. Now we have to apply some condition. What if the Rn is an infinity? The condition says if nth point n lies on infinity, that means Rn is at infinity, then the equation 3 becomes infinity instead of Rn. And 1 over infinity, as you know, is equal to 0. So we put down 0 over here. And we can say simply as the work done from R1 to Rn will be equal to minus Gme divided by R1. We call it equation number 4. For generalizing, we can say if we want to displace the body from the surface of the Earth of the radius Re, then we replace R1 by Re, and equation 4 becomes, which is the radius from here to here, it becomes, for the equation, delta work or the work done to the surface of the Earth will be minus Gm, which is the mass of the body, into Me, which is the mass of the Earth, divided by Re, which is the radius of the Earth. Now, actually, it is the work done against the gravity, so its value is always taken as negative, because we were moving the body against the gravitational pull. So there is a negative sign over here in the case of absolute potential energy. So let us define absolute potential energy now. The absolute potential energy is given by the statement: the amount of work done in moving a body at a certain point in gravitational field to a point zero potential such that the body is never accelerated is called absolute potential energy. Now let us define gravitational potential as well. The gravitational potential at any point is defined as the potential energy per unit mass at a point which is distance r from the center of the earth. Mathematically, we can write it down as gravitational potential is equal to absolute potential energy divided by mass per unit mass. So we can say Gm, which is the mass of the body, Me, which is the mass of the earth, divided by r, which is the radius of the earth, divided by m, which is mass. So these two masses cancel out, and what we are left with? We are left with the gravitational potential is equal to G, which is the gravitational constant, Me, mass of the earth, divided by Re, which is the radius of the earth. In this way, we can calculate the gravitational potential as well. Inshallah, we'll meet again. Allah Hafiz.